process called photogrammetry, or that's what it is called when you generate 3D images. And we didn't expect to see any wood because it had been on the seafloor for so long, but there were a few pieces that were poking up out of the sediments.
Might get a move underway, Andy, if you're good with it.
So maybe they had been buried enough
Sirius turn to starboard, so we're going to go kind
not
of north.
to be exposed to those mollusks.
Bridge is RV
There
now.
was very little left of the structure of the ship. It was
30
mostly
meters, bearing 25
the ballast
degrees,
piles
speed decimal 2.
and a few other artifacts. And
correct.
it's like a cooking pot and
Thanks,
a
Bridget.
vase. What else did we see? We saw a pile of conch shells that was interesting. Suggesting they had either collected them maybe in the Bahamas or they were using them as food.
You see that upper left edge?
Or they might have been merchandise that they planned to sell someplace.
Right.
Go ahead.
So there will be some great video on that posted on the web soon, and photographs.
Looks like the top edge of that piece of wood might have had some burrowing organisms, possibly shipworms.
You had a good eye to identify that as wood from a distance. I thought it was a pipe.
Some days you get lucky. That's all it was.
Video's clear.
Come on out.
So that probably hasn't been there very long, you think? I mean, it's hard to say, but
yeah, it is hard to say.
It would be broken down if it had been there for many, many years. Also buried by sediments. There's so much sedimentation here.
Sometimes, yeah, it depends on the subject. All right, Sirius, I got a ship going. Sirius is heading there towards you. A 30-meter move. Looks like we are.
One of the resources that we use to select dive sites is, of course, we map in high resolution the seafloor using multi-beam sonar, and that gives us a record of the water depths. But it also has a signal to it called backscatter intensity, and that's the strength of the acoustic signals returned to the receiver. So a sound pulse is emitted, bounces off the seafloor, and returns to the vessel. And the length of time for that return tells us the depth, the water's depth, but it also, the strength of that signal tells us what the substrate character is on a very broad, general term. If it's very hard, I'll stop so you can talk about this.
Oh, I was just wondering if that's another one of the low bait.
It does look like it.
Ctenophores.
Beautiful color.
Yeah, what a gorgeous color.
Gosh. We haven't gotten a look if it has the combs. Yep, it does.
There it does. Wow.
I wonder if the other one was that color. We just couldn't see it as well in the water column. That's pretty brilliant purple.
I think there was another one too, somewhere. It's gone.
Maybe it floated by in the current or something.
Yeah.
So you can imagine if sound were to bounce off of this substrate or this type of seafloor, a lot of it would get absorbed by the sediments, and it wouldn't reflect as much sound as if this were a very hard, flat, rocky surface. And so the backscatter intensity signal, if we map that out just as its own map, can sometimes give us really good information as to how hard the seafloor is. we haven't generated that type of map yet for this area, but we have used it in the past for some of the areas we've explored. And it's always interesting to get new information on what the maps tell us and what the substrate actually looks like. So this is called ground truthing, our hypothesis of what the seabed character is. And so now we know that this seabed is not hard rock, and it wouldn't send back a very strong reflected signal. And so we'll have to check out the backscatter and see what that data tell us. We have an amazing mapping team on board here, led by Derek Sowers, who I was going to introduce, but he's working hard, looking for the next site. And we also have Kevin and Scott. I'm not sure of their last names, but they run the night shift. And every night between dives, we run the multi-beam, and we go and map areas that have not yet been mapped. And at times, those areas are sites we're going to select.
Go ahead.
This looks like a
Holothurian.
This might be our first
sea cucumber.
Yes.
He sure does blend in well.
Gosh, no kidding. And for many of you, it's probably hard to believe that this is related to sea stars.
Yep.
And brittle stars and crinoids and urchins. But if you were to look at the end, you would actually see that it has that radial symmetry. And it does have a spiny skin. You can see the knobs of the spines, putting it into that phylum Echinodermata, or spiny skins. And we've had some adventures with these.
Let's go all the way to the right.
In this expedition. In one of our deeper dives, we witnessed the defecation pattern of a Holothurian, and they made a very interesting fecal trace.
Okay, when you're clear,
that seemed to be characteristic of the species, because there were several in the area, and we saw several of those fecal traces. And we called it the Holothurian outhouse. And then we saw it again later, near to the wreck, near to the chain of the anchor chain of the wreck.
All right, looks like waypoint 3 from the sled is 344.
344. We still got moves going pretty constantly.
I think we just came to our stop. Almost there.
And I think we were talking earlier about these canyons, and that we're kind of at the southern part of the canyon kind of territory, which goes all the way through New England. And there are 13 canyons in the mid-Atlantic region.
I
guess we're a little bit south of the mid-Atlantic here, right?
Understood. Range.
Yeah, the mid-Atlantic bight
is
a bight is sort of a embayed area, or often V-shaped, but in the case of the mid-Atlantic bight, it's more U-shaped. So it has geographic boundaries, and the tip of Cape Hatteras, I believe, is considered as the southern extent of the mid-Atlantic bight in the mid-Atlantic region. So we're just south of it.
And these canyon features can be quite impressive.
Where's
They
that
vary in
right
shape
here
and
to the lower right?
even how they were formed. Some of them are from old
that?
river flow,
Oh,
right? And others are just
tripod
from
fish.
collapses and sediment flows.
Yeah, they're different origins for different canyons. Some are very obviously the extension of a river channel, the Hudson River, between New York and Connecticut. You can follow that channel all the way out to the edge of the continental shelf and well beyond the margin into waters 5 kilometers and deeper.
It does appear that way. That's
And now,
how
that
Yeah,
doesn't
we'll
mean
take a
that a
look at
river carved it, but it's certainly influenced
Also
by
a
the
tube walking
bottom-hugging
there on the left.
currents that flow down through it. A lot of these canyons potentially had origin from faulting during the expansion of the Atlantic in the early years of the growth of the Atlantic.
And another example of marine debris. It has
Sprite.
a tiny little gastropod on the right. And a sea pen.
It's trying to look like a holothurian,
Yeah.
getting all covered up.
Copy that. Come on out, video.
And so these canyons basically funnel sediment down to the deep sea. And they can have very steep walls that are made of different types of rock or clay-like material. And those are often inhabited by especially octocorals and some scleractinian corals.
Yeah, the carving of these canyons, once they've been initiated, it causes sediment-filled bottom waters that, because they're rich with sediments as they start their motion, they are denser than the rest of the seawater, and so they form a density current as they get channelized into these canyons. And of course the canyons are steep in areas, but they are flowing down slope, and these density currents begin to pick up speed, and with the speed they start picking up more and more particles, and they then become very erosive. It's like taking sandpaper, cruising down some of these very steep canyon walls and eroding into them, and those are known as turbidity currents. They're very turbid or unclear waters because they have enough velocity to keep all that material in suspension, and that material just abrades the walls and helps to erode these canyons. So as you erode deeper and deeper into a canyon, then the walls above it get steeper and steeper, and sometimes they become unstable and pieces of those walls break off and contribute more material into the downward motion of the material.
It's another urchin. It looks like he has a piece of seagrass.
And again, he's sitting on what looks like some coral rubble. Cemented coral rubble.
See the long tube feet?
Still down.
And so due to that influx of sedimentation, the canyon areas are considered highly productive compared to other areas outside of canyons.
Blown out partial.
Well, they are certainly bringing current and
that object at the bottom.
Stirring up the waters and allowing material to
come in on
it. We just said, there's. Pilot, if you could zoom in on that little pile.
I think this might be all of our zoom in this location. I can move forward a little bit
down,
though. Looking at the stuff.
It's just off the picture.
Right
yep, that is one of those holothurian fecal piles.
There's a holothurian attached to it.
I think that's him right there. Yeah. That's him.
Oh my gosh.
He has really camouflaged himself well.
So these holothurians, the sea cucumbers, ingest the sediment and utilize whatever food is available in that sediment, and then it comes out the back end and in a little stream, a tube pattern, and then
copy that video. Come on,
holothurian zigzags back and forth to make that pile.
Okay.
I don't think that would be fossilized in the rock record, but if it were, now we'd know what made it.
Yeah.
If it's fossilized, it becomes a coprolite.
Move complete. Thanks, Bridge.
That is fossilized poo.
Yeah. Ooh. Okay.
These turbidity currents are really interesting because they not only scour the canyons, but they really are the delivery mechanism for taking sediments from the continental shelf, which are largely coming from rivers off the land, and channelizing that material and delivering it to the deep sea. And when those currents hit the flatter portion of the continental margin that we call the continental rise, the velocity of the current declines very rapidly, and those sediments immediately fall out of suspension and deposit on the seafloor. And in some places they create broad fans of deposits. In some places they just keep carrying, that turbidity current keeps moving down through if there's enough power behind it and channelizing. In fact, tomorrow's canyon is one of those that the canyon just extends very far offshore. And it's amazing to me that a canyon can extend that far. I don't know where it gets its power from to erode into the material, into the seabed. And we'll hopefully have Jason Chater from the USGS and my colleague Scott Harris on board when we are looking at the geology of that seascape. And sometimes these continental margins, of course, they can experience earthquakes, and those earthquakes can cause detachment of some of these steeply sloped areas, and that sediment can detach. Sometimes it's actual rock that detaches and it becomes unstable, and if a lot of that material quickly descends to the seafloor, it could displace enough water to form a tsunami. And
looks like you're
the U.S. Geological Survey in Woods Hole has done a lot of investigation of this continental margin, mapping it in detail, looking for areas that show evidence of large-scale slumping, we call it, that might be an indicator of past earthquake-induced activity. And
I think there's actually a waypoint 4, so
it's been very interesting.
Keep us moving.
Understood.
Until we see
it's very hard to age date anything like that or when it happened. And of course, you don't know how quickly large masses of rock fell to the seafloor or fell into the depth.
Quick zoom here, video.
Bobtail squid? Nope.
Yeah, like a ship move range 30 meters, bearing 350 degrees.
We're both looking up our noses.
Sorry, I cannot hear you at all. Video. I got a lot of people in my ear.
That's correct.
Can we set it between our skids?
Yeah, we can definitely do that. Just give me a second here while I float around it.
Formosoma placenta.
Looks cool.
And those pouches that have a little spine at the end, Chris Ma informed us that there was some other researcher had suggested, and I wish I knew who that was, I don't have his name written down, that those pouches might be used to be more like hypodermic needles to poke into potential predators.
And they have a type of venom in them.
You want to cheat.
So this wouldn't be something you'd want to go pick up with your bare hands. And these are also pancake urchins, so if you were to take them out of the water,
kick on the extra lights.
You can try it.
Get rid of all their water, and they would flatten out like a pancake.
Whoa. What are those sacks on there?
Quite beautiful.
And you see those little white glove type of tips to some of the spines around the edge. And our colleague Stephanie Bush let us know that those are little jaw-like spines.
Pedicelaria.
Pedicelaria, yep. And were those the features that were used to help keep the surface clean? I didn't catch all of what she said. Or is that the other spine?
No, those can definitely remove things from the
yeah. So
what are we going for here, video?
It's those little white,
white
tips.
glove.
The legs here.
Yeah,
white
but the
tips on some of the legs.
The spines on the top of the legs.
I got you.
Edge, yeah.
We saw some of them open. They are like little jaws. You can see how the water vascular system pumps water into the tube feet, tube legs.
One open in the lower center.
Give it the mobility it needs. Hello. Who do we have online?
Hello. Sorry. Hi, it's Scott.
Hi, Scott.
Oh, hey, Scott. We have Scott Prance online. Scott is the science advisor.
I never introduced myself. Sorry.
No, you don't.
Scott Prance, Geology, University of Louisiana, Lafayette. And I'm calling in just because I saw a coral that I haven't seen today. Maybe you've seen it in the chat room, but it's off to the left, so when you're finishing getting these nice images of this urchin, we could have a look at it. It's white, and it has a brittle star on it.
Oh, I didn't even see that.
Slight tilt. There we go.
Thanks for pointing that
out,
Scott.
It's pretty small.
Okay.
Not much taller than this urchin.
That's great, Pilot.
Okay.
Beautiful view.
Come on out, and I think it's just to the left here, right? Is it
that?
Is it that?
Yep.
On the left.
Okay.
I believe.
It does look like a brittle star.
Correct, on the left there.
Yeah.
That's a partial, by the way.
Oh, okay.
And it's probably going to be a sea pen, but I just want to verify.
Yeah.
Because there are a couple of other octocorals that can live in sediments like this that would grow like this, both bamboo corals and a type of chrysogorgiid called radicibes.
Looks like the ship is
20
meters. I guess you can get a little bit of rotator off. Be all right.
So Scott, is this something that you've seen before? Is the brittle starfish and a sea pen, being on a sea pen?
Yeah, in fact, up off the Aleutians, we see this very, very commonly on the genus Helipterus, which is another kind of sea pen. And these brittle stars will basically crawl up and then they'll stream their arms out into the water, just like a fishing line, and are presumably capturing plankton in the water. So this might be actually a much larger version of those small, what I was calling red sticks before. So this could be Distichoptilum. Thank you for having a look.
Video's clear.
Copy that. Come on out.
Thanks, Scott. We've missed your voice.
We haven't had too many octocorals to look at today.
No.
None, actually, so.
We have a few questions from the North Carolina Aquarium crowd that Joe Hoyt is hosting, and we want to say hello to them, first of all, and thanks for tuning in and watching and following us. One of the questions that I will...
Yep, I'm on my way.
There's one that I'll ask of the pilots in a moment.
Move complete. Thanks, Bridge.
We'll wait a minute, but in the meantime, one of the questions is, what is the rarest animal you have seen so far on this dive, or maybe we can address both this dive and the cruise so far.
Copy. It's pretty much uphill for you.
I'll let Cheryl, the biologist, answer those.
Well, it's kind of a tough one because we've seen multiple, I think, of just about everything that we've observed.
Somebody, yeah, Watchlead's calling you. Go ahead, Watchlead.
Sure. Sure, absolutely.
So while we're thinking about the rarest animal question, I have the pilot ready to answer the other question. It says, what is the largest hazard to the ROV while exploring?
Okay. Which do I need to be on OKEX?
Yeah, that'd be great.
Okay. The largest hazard would probably be the man-made trash and things like fishing line and things like that in the water that could easily get tangled up in thrusters. The other ones we can plan for, such as pipelines or infrastructure built in. You know, we make sure we dive well away from that to keep safe. But the one that we can't plan for all the time is that garbage, and it's mainly things like fishing line and
fishing gear.
Fishing gear, yeah, fishing line and fishing gear in general, because that could get sucked up on thrusters, and then we'd lose control of our ROV.
We'll get stuck on the bottom.
Well, yeah, we could even possibly get tangled up in it and stuck if there's a hanging wire or something that we did not know about over us.
Could damage the vehicle. Could do a lot.
It can be quite scary when we run across that if we're not very, very careful about it. So we keep a constant lookout for things like that to make sure that we don't get ourselves in that predicament.
What about natural hazards?
Well, natural hazards could be considered things like canyons, and depending on the currents of the day and, you know, how we're having to have the ship line up, because the ship might have to fight some forces and it may not be favorable for the ground terrain that we're seeing. For instance, and you can imagine if we had a sheer face and the currents were trying to push the ship into it and anything were to happen, we could potentially be dragged directly into that if we weren't ready and watching for that kind of thing.
Yes, the key thing there is we can come up on the winch at around 30-35 meters a minute. So if we have a cliff that's, say, 50 or 100 meters tall, that's going to take us, you know, 3, 4, 5 minutes to get over on top of it, and the ship can move very far in that amount of time.
Thanks a lot, guys. It's great to hear directly from you. Would hate to guess what your greatest hazards are. I wouldn't have even thought of marine debris, so it's very, very important for these younger audiences to hear too. Thanks very much.
And just to add to that, one other thing is floating marine debris as well. I mean, because that can interact with the ship thrusters and cause us direct problems subsea. So floating or subsea marine debris is always bad. Is that what you liked, video?
For the ROV team is, what is the deepest that Okeanos can explore?
Well, the deepest that D2 can explore is 6,000 meters. We are 6,000 meter limited ROV, but that actually puts us in most places around the world.
Very good point.
Almost keeps you out of the depths of the Mariana Trench, but you actually did explore.
We did.
The shallower
we actually got to get to 6,000 meters there. So
pushing the envelope.
I think the mapping team can map down to
would you my lights?
12 kilometers, but I believe their primary accuracy is best from 10 kilometers and under.
They when we went over the Marianas Trench, they sent pings down and got nothing back. So in the Marianas is 11,000 meters, 10,000 meters.
11, I think.
So I think the mapping team can speak more on this, but I think their limited is 8 kilometers, something around there.
What is that?
We've
actually Go for a zoom video.
Derek in the back, if he wants to get on and tell us about it.
And yeah, Derek said, I just asked him, and he said that 8,000 meters is kind of the limit of our mapping ability on Okeanos.
My speed junk. still got to move in? Because I can hop ahead easily.
6,000 meters
that we were
is
just
about
looking
4
at are
kilometers, by the way.
Anthoptilum
I think it's about 6 kilometers.
grandiflorum.
4 miles.
And they have a characteristic question mark shape. And that one did look like it was a question mark.
Got a couple of sea stars coming here in the distance.
And the brittle star was probably Asteronix, or a relative of.
Yeah, I'd like to move range 30 meters.
And another question is, what are the little bumps on the seabed? And that's a very good question. They are likely made by some organism that lives below the surface, but we don't yet know who makes that. But they certainly are very prevalent in this area. At the beginning of the dive, where the slope was a little lower, we didn't see them.
Oh, come wide.
But we've certainly
I'm gonna land. Do you want to see the ship
plenty
or
of
that?
them for the dive.
Oh, okay. Nothing real.
Another question here from the North Carolina Aquarium is, what's the hardest part of working in deep water?
Is that for us?
Yeah, well, if you want to give an answer, that would be great, and then we can.
I was going to say breathing.
The pressure. It's so much pressure.
It's very stressful.
Very stressful. No, actually for us, it would be the delay on our winch movements. So we have to move the ship, and then it can be up to 15, 20 minutes of delay before we'll get serious moving. So we need to plan that far ahead on everything we're doing.
Wow, yeah.
Compound that with things like steep cliff faces, and we're busy. We're very busy.
And that looks like an umbellula sea pen, possibly.
Yeah, we saw one of those at the very beginning of the dive, and I think that was the only time.
Mm-hmm. I'd say from a biologist's standpoint, the hardest thing is finding the resources to get out here to do this. It's very expensive work to have the technology that we're using here on the Okeanos. And so it often requires building teams of scientists that can put together really nice products from the time at sea. And having collaborators, strong collaborators, is definitely the way to go, so that you can actually use the cutting edge technology such as the D2 ROV.
Let's tilt up and get the white portion.
And D2 stands for Deep Discoverer. And if you haven't looked at the online photographs of it, it's a monster. It's beautifully designed, and but it's also very large. And I don't know if the photographs really, I don't know if any of the photographs have a person standing by them. I know when I first saw it in reality, I was shocked at how tall it is.
Okay.
Leslie, sorry to interrupt. I just want to point out the polyp that you're looking at here looks like it has one tentacle curled into the mouth, which could be an indication that it's captured something and is feeding. That would be the way that they feed.
Oh, that's really interesting.
Also worth noting for the folks who are watching, this umbellula is a kind of sea pen, and we were just looking a few minutes ago at that question mark-shaped sea pen. So they're both in the order Penatulacea, and what they have in common is that they live in soft sediments. They're adapted to live in soft sediments, and so the base has kind of an anchor to the colony that can be inflated, and so holds it in place without being attached to a rock.
Well, this is a good spot for these guys then.
Absolutely, very characteristic of soft sediments where there's enough food.
And we've seen them.
See, normally these polyps, they have 8 tentacles that ring the mouth. You can really nicely see the mouth on that lower polyp, but you see the one on the upper left. One of those tentacles appears to be missing.
11, so it's pretty close to 12. So it's
curled over.
Oh yeah, I'm right.
Oh yeah, upper right is missing a few.
Boiling.
Yep.
Looks.
Boy, the lights reflect on that
central
portion.
Like the upper frame. Get closer up, I think would be.
Yeah. So if you have
another question from the North Carolina Aquarium is, what happens to all the data that is collected from the ship?
Slight tilt down.
And this is a very unique ship for that question, because the data, all of the data, becomes public very quickly. Of course, anybody can look at these videos and watch our exploration of the seafloor in real time,
about 7
just as we are, and that's becoming a little more common. But there's only a few platforms that do that kind of telepresence, and this is definitely one of the premier ships for that.
And Cheryl, to add a bit more information to that, all of the data that's collected by the Okeanos Explorer is publicly available through the National Archives within 60 to 90 days after collection.
Sorry, watch these. I had people in my ear. Did you say you want to zoom on this? Oh, that? Okay. Something happened.
Yeah, this might be a clue as to what is making these mounds.
That definitely looks like, well, I think it looks like fecal material, but...
Did you see that little
eruption?
Yeah,
and there was a little eruption of the mound, yeah. So maybe it's expelling its fecal material. Maybe that's what the whole mound is made of, who knows? Of course, the fecal material down here would be largely the sediment. These organisms probably ingest a lot of the sediment in order to get their nutrition. But we don't know what organism actually made it yet. Those are interesting. It has a ridge to it.
It's like, it's kind of shaking, so I'm thinking it's hollow inside the mound.
That might be you shaking.
I think it's me?
Most likely your thrust is
definitely
vibrating.
seems like it's shaking.
Maybe.
Or that shimmering water.
That could be shimmering.
I'm willing to go out on a limb here and say that this has been produced by an acorn worm, an entrepreneur worm, based on how smooth that is and that groove down the center. And I think maybe, Leslie, you said this before, but one of the things that's kind of interesting about this is obviously a lot of sediment that's been packed and passed through the gut of that worm and then redeposited. And it shows us how that the animals are able to sort of scramble up the sediments, they rework the sediments, they reorganize it, and then how long they just stay in place here. If there's not a lot of rapid current sort of blowing the stuff around, it just stays in place.
I want to keep moving now.
Yeah. And that is some major bioturbation. That's what we call that process of disturbing the flat-lying sediments. And as a geologist, it means that the sediment record is being stirred up and mixed up. So it's not always a good thing if you're trying to unravel
my craft has drooped.
Earth's history by looking at sediments, because the organisms have stirred it up a little bit. I noticed another question by one of the North Carolina aquarium folks. Why are so many of the creatures red? And I first want to say that that's a very good observation. We haven't seen a lot of creatures, but many of them have been bright red. And the reason I want to point it out as a great observation is that is so important to be good observers if you want to understand. You have to first use your eyes, use whatever senses you have, use the data. Those are all observations. And from those observations, we can begin to make interpretations to understand. That's what science is. So after saying that, I'm going to pass that observation over to Cheryl, because she has a great answer to the red coloration, because she's explained it before.
Yeah, we've been talking about it quite often because we see so many red organisms.
It was called in 1803.
We don't have anything after that?
Sunlight or light hits the sea surface and starts getting deeper. Red is the first color that's removed, and so when you dive to 30 feet or so, things look more blue. Some of the red is already being absorbed by the water instead of making it further. So in this very, very low light environment, red basically appear black. So it's a way to camouflage and blend in with the dark environment.
Good copy, Bridge. Thank you.
Red has a longer wavelength than, say, blue has the shortest wavelength. So that has something to do with the physical characteristics of why red disappears first. What I find interesting, though, is that the seabed is not dark here. So it's really not that helpful here. And also there's no light at all. So I still don't really understand why an organism would benefit from being red.
Well, we think of it as absolutely no light, and at this depth there really isn't any light from the surface that reaches, but there are animals that bioluminesce. There's quite a few, and so there might be little flickers of light here and there, and if you just blend in with the black darkness that's all over, you are going to disappear into the black, basically.
Is that a coral?
Is that a what?
It's not a sea pen.
Oh, and that one has an ophiuroid at the base.
At the base, holding it up.
Look at that.
This one is another sea pen, maybe the genus Helipteris. Or Tylum or Anthopilum. It's really hard to identify some of these sea pens unless you have them in your hand under a microscope.
And it's interesting that it has a little brittle star associate that's wrapped around the base of it. We've usually seen the brittle stars higher up on the organism where they're probably able to grab some food from the water column, but this brittle star is wrapping around its base.
We do it with the extra lights.
Sure, let's go ahead and try that.
Oh, and there's something at the tip of this sea pen. Or maybe that's just the growing end. And one of the polyps is retracted.
Yeah, that looks like it's retracted up there. It is definitely the growing end.
Yeah, we got
a lot of sediment coming in, yeah.
Kill the lights.
And I'm downstream a little bit. Actually, look up here.
Oh, great. Look, so now we're seeing a little more current.
Look at this.
Left straight up.
And I say great because I'm hoping for areas that have been swept clean of sediments with exposed rock. And therefore, coral habitat. And it was just a localized cloud.
Sorry, I was trying to talk to you guys. I had a delay in my iris.
But there's plenty of material in the water.
Well.
A lot of it is sediment, of course, suspended from the currents, but a lot of it is also what we call marine snow, which is the mucus and fecal pellet material and shells of organisms that have died, and it is the constant rain of material from the sea surface all the way to the sea floor, and often it aggregates into large masses, and those are the big snowflakes, marine snow, and that helps it to sink faster, but it also helps deliver more material, more organic material, and thus food to the deep sea. We have a whole discussion going on related to that fecal pellet trace that we saw earlier. It's not a pellet, it's a fecal trace. It was more of a tubular kind of thing, if you missed it. But it could have been made by a polychaete, a terabellid polychaete. Les Watling writes this, that currently has its tentacles pulled in. Okay. And there was a second lower mound to the left that made him think that it was a terabellid.
It's the grass.
Come on out.
And that the two grooves along the sides of the pellets must also be distinctive. He knows that when they fed pink particles to a local mudflat terabellid, the particles all were arranged in a nice little line along the pellet side. Organized pellets. Organized fecal matter. Interesting. Fecal pellets and burrows and grazing trails, these mounds, if any of these things are preserved in the sedimentary record over time, we can use them as indicators of the organisms that lived there without having the fossils, so we can get a sense of at least what type of organism
I was hoping.
lived there. Those are known as trace fossils.
Pretty far ahead there, pilot, or?
Can't always conclusively say who made the remains, but you certainly know if you had burrowing organisms, or sometimes the fecal pellet remains do give us a clue as to what organism left that trace behind, literally.
What's that?
That's a good question.
More debris.
It's another motor. No.
Is that a bigger small log?
Oh, what?
See here that there's a small log you guys found.
We did find that. Let's come in video.
Oh, it's a bucket, maybe?
It's a rubber, maybe?
I think so.
Whoops, there we go.
And it's a bunch of different organisms have made use of this structure. Anemone and lots of brittle stars on it. And it's highly sedimented, so I guess that means it's been here a while.
It's not deforming like rust, so I wouldn't think it would be iron.
Yeah, I wonder if it's a rubber bucket
it looks, yeah,
instead of a metal bucket.
It's the community center.
Pulling out for full.
Yep, come on up. I was trying to trace around it to see if it was anything recognizable.
It does seem to be rolled up on the right-hand side.
It's kind of got some ridges on the side. Maybe it's not really a bucket, but a cover or something, or...
Can you pirouette in that direction?
Yeah.
Looks like it's a man-made object, for sure.
What was that last move at?
The last move has stopped. It's been stopped for about 3 minutes.
What was it?
340.
Thanks.
30 meters.
Yeah, you can do another one.
Copy that. Co-pilot, you ready?
Go ahead.
All right. Bridge, this is ROV nav. We'd like to call on another move, 30 meters at 340 degrees, speed 0.2. Good copy, Bridge. Thank you.
I think Watchlead's calling you, Nav.
Stand by one. I will calculate it now.
Okay. You good there, video? Or do you want another side of it?
Good
I think
enough.
that's probably enough.
Watchlead, this is Nav. We have about another 1 hour and 18 minutes until we need to come off bottom.
And we've just learned from Nav that we have about 1 hour and 18 minutes left of the dive. So we're going to keep ascending this backbone of the steeply sloped ridge, sloped on the sides. The backbone is more gently sloped. We have seen very little variation in the substrate. And we began at a depth of 1713 meters, and we are currently at 1557 meters. So it's been a steady climb, but without too much change in the substrate. Our friend the cutthroat eel. Quite common in this part of the world. We've seen them on many of our dives. A lot of them in the coral mound areas. They found great habitat among the coral branches and the framework of the smaller mounds made by dead coral rubble.
And the North Carolina Aquarium is signing off, and thanks so much for joining us for a while today and having those great questions for us. I hope you'll continue to explore.
And thanks again, Joe, for sending us those questions.
Mm-hmm.
Joe Hoyt.
Turning back around, coming back for my next pass. Getting a little steeper.
A big snail at the bottom, lower left.
I have a lot of dust that's going to be coming in. Probably won't. It's not going to make a good video. It's going to cover it.
It's going to be very good to see. He's really stretched out for our gastropod specialists.
It's not going to be a good video.
Yes, definitely. So I believe what I was told is that we're heading up to waypoint 3 and then continuing to waypoint 4. Is that correct?
Am I pulling you?
Copy that. We will go directly up the slope then. Yep. So pilots, we just had a request to head directly up the slope rather than heading to the waypoints directly. So if you wouldn't mind turning to face what you believe is upslope, we can get a decent reading off of that.
Where are you in that move?
We're just about done. It's probably another minute or so.
Okay. Then yeah, it's going to be, you can see on sonar that it's going to be right here.
Yeah.
I can't really push out though yet.
No, copy that.
Whoops. Anyway, it's going to be about 285, 280.
Your copy, Bridge, thank you. You said 285, 280?
Yep.
All right, excellent.
Looking at Sirius, it's probably 290.
It gives you an idea of how disturbance in the water, think of a current coming down, picks up and suspends that material.
285.
And the faster flow, the greater the grain size and the more erosive power a current would have. And that's what has formed, eroded, and shaped these canyons over millions of years.
I'm going to get above this. How far was the ship move? 30 meters?
Yes, I have not put it in yet. The ship is currently stationary.
Yeah,
Are we ready to go?
Yeah.
Copy that. 30 meters at 285. Bridge, this is ROV nav. We'd like to make another move. 30 meters at 285 degrees. Speed 0.2, please. Good copy, Rich. Thanks.
And while we're making a little bit of a move here with the ROV to get to the top of the crest of this ridge, might be a good time to call out all the help that we've had today in the chat room. We've had Adrian Copeland from NOAA and Alan Leonardi from NOAA, Alexis Wenning from Temple University, Andrew Quattrini from Harvey Mudd College, Asako Matsumoto from Japan, Jason Chater from the U.S. Geological Survey, and Jill Bork is also from the U.S. Geological Survey. Jim Masterson, not sure where Jim is from.
Florida Atlantic University and Harbor Branch.
Great. Les Watling from the University of Hawaii, Megan McCullough from the North Carolina Museum of Sciences, Michael Vecchione from the Smithsonian Institution, and Nolan Barrett is from South Carolina.
Okay, gonna push out.
From the Medical University of South Carolina Natural Products Discovery Lab.
Here.
And we have Bob Carney from Louisiana State University, and Scott France from Louisiana State at Lafayette, and Scott Harris is from College of Charleston, and Tim Schenk is from Woods Hole Oceanographic Institute, and Tom Hansknecht, I don't remember where he's from.
I don't have that either.
Okay, I think I might have it. I will look.
Just to correct you there, Cheryl, it's the University of Louisiana at Lafayette.
Okay, great. Thanks. Sorry.
That object just to the left.
Over here?
Maybe just sargassum. Not sure.
And we've also had Tara Luke from Stockton University in New Jersey.
Go ahead.
Steve Oskovich at Temple University.
Yep.
Sandra Brook from Florida State University. Nick Polenko from NOAA. Not sure which office. Sorry, Nick. John Reed from Harbor Branch Oceanographic. Heather Judkins from U.S. University of South Florida, sorry, in St. Petersburg. And Daniel Wagner from NOAA OAR, who was there with the Patriots Point group. And Andrew Schuler from NOAA.
Copy that.
And Amanda Demopoulos from the U.S. Geological Survey. I might have repeated a few. I was trying to check through my list, Cheryl.
Yeah, that's great.
But that's quite a good number for the day. And Zach Proulx, also from the College of Charleston. He was in Peter Atnoyer's lab, which is one of the ECCs, or the Expedition Control Centers.
Still camera.
Not, well, it's not the right angle, but we can try it.
It's not. The still cam is focused to right between the toes now, so it's actually too far.
Let's kick on the extra lights. So we get enough overshoot.
Would you like the extra lights, pilot?
Yeah, go ahead.
Coming on.
Not that much for that distance.
Yeah, it's a little high. I didn't want to get directly over it because I can get more of a profile this way.
Video's clear.
Come on out.
Lights are clear.
Lights off.
Thank you.
Something floating lower left. See the strand? Is it attached to you?
There had been a suggestion that we might want to dig into one of these mounds, and unfortunately that would create such a disturbance in the water we wouldn't see anything. And I don't think the currents would be able to clear the water in time for us to really know who lived there. So
I like to listen to video.
We've opted to keep climbing, and we're a little behind on reaching our waypoints. So having only about an hour left, we're just going to keep trying to get up this ridge.
All right, Sean.
The backbone of
Ship's
this
on the move.
steep